Hello. In today's topic, we're going to be discussing um, what's known as the addition rule for probability. Before beginning that, I'd like to expand real quick on something that we discussed in the last topic, which was the multiplication rule. And really, the multiplication rule, it used inherently the idea of independent and dependent events in something called conditional probability. And in conditional probability, most of the examples that we did in the last topic, they were just assumed that you could do in your head. You needed to know that if you had already drawn a card out of the deck, there was one less card in the deck, and so that's going to affect the probability of getting whatever card you would like on the next draw. I would like to show an example of where conditional probability is calculated, and it's not just a mental math situation. And all it is really, it's a reformulation of the multiplication rule. The multiplication rule said the following. It said the probability of A and B occurring is going to be the probability of A occurring multiplied by the probability of B given that A has already occurred. If I solve this formula for the conditional probability, this piece right here, all I need to do is divide both sides by the probability of A, and I'll get this formula shown in the box here. And that's actually our mathematical formula for calculating conditional probability. If I want to know the probability of B occurring given that A has occurred, I need to find the probability of A and B occurring divided by the entire probability of A occurring in the first place. That formula is used a lot in medical fields because there's something in medical fields called false positives. So here's an example of where conditional probability is used, and it has a major application. So this situation says a certain virus infects 4 out of every 100 people. So 4% of the population just naturally have this virus. A test to detect the virus is positive 98% of the time when the person has the virus. So it correctly identifies the virus 98% of the time, and 5% of the time when they don't have the virus. We call this a false positive. So what that means is 5% of the time when somebody takes it and they don't even have the virus, it's going to actually say that they do. And that's what gives a false positive. So we'll see what the side effects of that are. So given a person takes a single test and it's positive, what is the probability someone actually has the virus? That is, what is the probability that they have the virus given the test was positive? And what we need to do is we need to calculate the following. I want to find the probability that they have the virus given they got a positive test. So you get a positive test, what's the likelihood you actually have the virus? Because 5% of the time, when somebody doesn't have the virus, they're going to get a false positive. So what we need to do is we need to find the probability of having the virus and getting a positive test and divide it by the probability of even having a positive result in the first place. So I go and I can use a tree diagram for this. Well, what's the likelihood of having the virus in the first place? We said 4 out of 100 people have it, so that's going to be 0.04. So 0.04, 4% of the population has the virus. The complement would be 96% of the people don't have the virus. It also said if you have the virus, 98% of the time it's going to say that you have it and it's going to give a positive result, which means, unfortunately, 2% of the time if you have the virus, it's going to say that you don't. If you don't have the virus, this was the false positive case, it said 5% of the time that you're going to have it, which means 95% of the time it does its job and says you don't have it when you in fact do not. I need to find the probability of having the virus and getting a positive. Well, that would be this branch right here. So I need to do 0.04 times 0.98. So you grab a calculator, and this is going to be 0.04 times 0.98. 0.04 times 0.98 tells me that's going to equal 0.038. Now I need to find all the different ways I could have a positive result. And there's two ways. I could use this blue branch. I could actually have the virus and get a positive, or I could not have the virus and get a positive. And that occurs 0.96 times 0.05. And I need to add these two because those are the two ways that I can get a positive. So this first branch was 0.038. This bottom branch, I need to calculate is 0.96 times 0.05, which is 0.048. And I need to add those two because those are the two ways that I could actually get a positive. So 0.038 plus 0.048 is 0.086. So divide this by 0.086, and this will tell me the likelihood that I actually have the virus, given that I got a positive result. So 0.038 divided by 0.086, and it tells me it's actually only 44% chance given just one positive test that I have the virus. And the problem is because it has a 5% false positive rate. So inherently, what do medical people do, doc? Well, they give another test and they say, what's the likelihood you have the virus given you've had 2 positive tests? Well, I would expect it's probably this number right here is going to go up. So what do I need to do? I just need to calculate another branch of this. So I need another positive test. So another positive test, well, if you actually have the virus, it correctly identifies it 98% of the time. If you do not have the virus, it will accidentally or false positive tell you that you have it 5% of the time. And then I just redo the calculation. I need to find what's the likelihood up top that I have the virus and I got 2 positive tests. Well, that's this blue branch. So I need to do 0.04 times 0.98 times 0.98. So 0.04 times 0.98 times 0.98. That's going to be 0.0384. I'll do it to a couple more just to be more precise. This one would be 96% don't have it, and then 5% to get back-to-back positives. 0.96 times 0.05 times 0.05 is going to leave me at 0.0024. So down here, what's the probability that I had a virus and had 2 positives? That's this blue branch, 0.0384. Now I need to divide it by the multiple ways I could have had back-to-back positives, and that would be the blue branch plus the green branch. So I need to add those 2 numbers. So 0.0384 plus 0.0024. When I add those together, I get a total of 0.0408. And if I divide those, I'll see I get 0.0384 divided by 0.0408. I'm up to 94.1% chance I actually have it, which means you probably have it then. And that's why it's important that we do, multiple tests in order to, assure that you actually have it, because there are things called false positives. So that's where conditional probability is very helpful in the medical field. And that really concludes the last topic. Now we can begin discussing today's topic, which is on the addition rule for probability. So in the prior lesson, we discussed whether compound events were independent or dependent. That is, whether the outcome of one would inherently alter the probability of the second event, whether it would affect the probability. But now we're just considering whether the 2 events can even occur at the same time, whether they can just occur at the same time. When 2 events cannot occur at the same time, we call those mutually exclusive. If you draw Venn diagrams for those events, they don't overlap. An example would be rolling a die. Event A would be rolling a 3, event B would be rolling a 4, and there's no way I can roll a single die and get a 3 and a 4. There's no overlap. It's impossible. Those 2 events cannot occur at the same time. An example of 2 events that can occur at the same time would be, maybe I select a student from the population and I want to know what's the likelihood that the student is female, is event A, and event B is the student plays tennis, and there is an overlap. That overlap would be a student who is a female and plays tennis, and there are plenty of those students. So those events are, we would say, not mutually exclusive. They have some overlap. So the first thing we're going to do is just practice using that vocabulary, identifying whether events are mutually exclusive or not. So situation number 1, event A is randomly selecting a female student. Event B would be randomly selecting a nursing major. Maybe this is at a college. Are these 2 events mutually exclusive or not? These are not mutually exclusive events. The reason why is because there are plenty of female nursing majors. Those 2 events can occur at the same time. Second situation, event A would be randomly selecting a blood donor with type O blood. Event B would be randomly selecting a blood donor with type AB blood. And these events are mutually exclusive because you can only have one type of blood. If you select a single person, they are not going to have O blood and AB blood. There is no person who has O and AB blood. What we're going to do next is calculate probabilities with mutually exclusive events. So if two events are mutually exclusive, then the probability of A or B occurring, all I need to do is find the probability of A and then add it to the probability of B, because they can't occur at the same time. So for example, and I understand in Monopoly you roll 2 dice. For our sake, just to simplify it, we're just going to assume that you roll 1 die. So let's say you're currently on Community Chest right here. What is the probability you land on free parking or chance? So you land on free parking or chance. Well, what do you need? You need the probability of rolling a 3 or the probability of rolling a 5. Since those events cannot occur at the same time, those events are mutually exclusive. All I need to do is add the events of the two events. So probability of 3 would be a 1 out of 6 probability. Probability of getting a 5 is 1 out of 6, so we get a 2 out of 6, which is a 0.33 probability. 2/6, 1/3. The next part would be, what if the events are not mutually exclusive? What if they have some overlap? So this isn't in the notes, this is just for you to listen in. So let's say I ask you, so you're going to grab a deck from, a card from the deck, and I want you to find the probability of drawing a 2 or drawing a diamond. So are these events mutually exclusive? Well, they are definitely not, because there is a 2 of diamond. So if I go, counting all of the ways I can get a 2 or I can get a diamond, I've drawn it for us here. And let's just count them. There are 1, 2, 3, 4. There are 4 2s in there, and I start counting there. So I've got 4. I've already counted 4. Then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 different ways I could get a 2 or get a diamond. But the problem is, the probability of getting a 2 is 4. The probability of getting a diamond is 13. And if I add those, I'm going to get 17. But I just counted, and there are 16 ways. And the reason is because if the two events are not mutually exclusive, there's some overlap, I'm going to count the middle item twice. Right? I counted it once as a 2, and I counted it once as a diamond. And because I've double counted it, when I add these two probabilities, I'm going to have to subtract out the middle, because I've counted it twice. And so the probability of getting a 2 is 4 out of 52. The probability of getting a diamond is 13 out of 52. And I need to calculate what's the probability of getting a 2 and a diamond, which is a 1 out of 52. And that's where I'm going to get 4 plus 13 is 17, minus 1 is 16. So I get a 16 out of 52 probability of getting a 2 or a diamond. If you want it as a decimal, it turns out to be 0.308. So we see if there's some overlap, if the events are not mutually exclusive, I have to subtract out that middle piece, because you're going to count it twice. You're going to count it once in this portion of the diagram, and you're going to count it another time when you count this portion, and you've therefore counted it twice. You need to subtract it out. We have a formula for this. It says if two events are not mutually exclusive, they have some overlap, I take the probability of A, I add it to the probability of B, and then I subtract out the probability of A and B occurring, because it was double counted. So note, this formula actually works even if the two events are mutually exclusive, because the probability of A and B in the case of mutually exclusive, well, in the case of mutually exclusive, this is going to be 0. So this part would just go away, and you would end up with the probability of A plus the probability of B. So this actually works for the case of not mutually exclusive or mutually exclusive. We're going to work just on calculating those. So you draw a card from a deck, state whether each is mutually exclusive or not, and then calculate. So probability of getting a 7 or a jack. Well, I can get a 7 and I can get a jack, but there's no such thing as the 7 of jacks. And so these two events are mutually exclusive. So there is no overlap. Probability of 7 plus the probability of getting a jack. I could subtract off the probability of getting a 7 and a jack if I wanted to, but like I said, that's going to be 0, because this is mutually exclusive. So I don't really need to do that. Probability of getting a 7 is 4 out of 52. The probability of getting a jack is 4 out of 52, and that is 8 out of 52. If you want it as a decimal, just because percentages maybe are easier to conceptualize, it turns out to be around 15%. Second situation, what's the probability of drawing a single card, and that single card is either a spade or it's a 9, and there is such a thing as the 9 of spades, so these events are not mutually exclusive. Because they're not mutually exclusive, you're going to have to subtract out the intersection, the overlap. So I need the probability getting a spade plus the probability getting a 9, and I need to subtract off the probability of getting a spade and a 9. Probability of getting a spade, there are 13 spades. There are 4 nines, and this is identical to the one that we led in with the 2 of diamonds. And there is one that is the 9 of spades. That's going to be 16 out of 52, which we saw earlier was 0.308. That's how you can calculate mutually exclusive and not mutually exclusive. I'm going to give you a chance to try. So your first job is to state whether this is mutually exclusive or not, and then calculate the probability. So the situation, quality control for a TV manufacturer has determined that 3% of TVs experience video problems, 1% audio problems, and 0.2% experience both video and audio problems. What is the probability a TV will experience either video or audio problems? And the reason someone would consider this is because that's going to affect the warranty, which we'll do calculations with in later topics. So give it a try, come back, see how you did. Okay, the first thing you should notice is that these events are not mutually exclusive because I said there are TVs that have both video and audio problems. So you're going to have to subtract out that overlap. There are 3% of TVs with video problems plus 1% with audio, but I've double counted the ones that had video and audio problems, so I need to subtract off the 0.2%. When I add these up, this is 4% minus the 0.2%, I get 3.8% or 0.038. So that's how you calculate this not mutually exclusive example. We can also use this in doing a two-way table. So we're going to do an example from the medical field of this. You're collecting data from a blood bank concerning their donors from the past 5 days. Find the probabilities of the following. What's the probability that someone has type O blood? Well, this is just making sure that you can read the table. There's 184 people that have type O blood, and there were 409 that came in. So 184 divided by 409, that's about a 45% of the population has type O blood. What's the probability that someone does not have type AB blood? Well, I'm going to use the complement for this. I know there are 16 people that have type AB blood, so I'm going to find what's the probability of someone having type AB blood and then subtract that from 1. So I know this is 1 minus the probability of someone having AB blood, which would be 1 minus 16 out of 409. 16 out of 409 is about 4% of the population. So 4% of the population have AB blood, which means 96% of the population does not have AB blood. And that's the benefit of using the complement here when they ask about not. This is where we're going to use our addition rule. Type A blood or type B blood. So I need to look here. Type A blood and type B blood, there is no overlap between those. If I used colors, let's go back and erase these ones that I've circled. Type A blood is right here. Type B blood is right here. There is no overlap between those. Those two events are mutually exclusive, so I don't need to calculate any intersection. I can simply do probability of having A blood plus the probability of having B blood and then add them together. Well, the first one's 164 out of 409. The second one is 45 out of 409. 164 plus 45 is going to leave me with 209. If I divide 209 by 409, I'm going to end up with about 51% of the population is going to have either A or B blood. Last one, what's the probability that someone has O blood or their blood is Rh positive? And if I look at those two events, there is overlap. So the first event was type O blood, and the other event was Rh positive. And when I do that, you will see there's this overlap. There's that 156. These two events are not mutually exclusive. They have some overlap, so I need to calculate the intersection. So what I'm going to have to do here is I need to find the probability of having O blood plus the probability of Rh positive. I need to subtract out the probability that someone has O and Rh positive because I've counted that once in O blood, once in Rh positive, I've doubly counted it. So the probability of someone having O blood is 184 out of 409. The probability of someone having Rh positive is 156 out of 409. And the probability of someone having O and Rh is, sorry, I made a mistake there. I realized it when I was doing the intersection. O blood, let's make sure. O blood is 184. Rh positive is 344. This should be 344. The intersection is 156. And then there's 156 out of 409 that had both. And I've counted that twice, once in O, once in Rh positive. So I need to subtract it out. So when I'm adding my fractions, since they're all common denominator, I just need to add the numerators. 184 plus 344 minus 156 leads me with 372 out of 409. Divide it by 409, and I get about 91% of the population is either going to have O or Rh positive. Last one, I'm going to give you a chance to try this idea of reading a two-way table with our addition on a mutually exclusive, not mutually exclusive idea, and see how you do. So you're working on a campaign for a politician and are asked to investigate how the population might consider a proposed tax on junk food. 1,048 people are surveyed and the results are shown below. Find the probabilities. What's the probability that the person supports the tax or is unsure? What's the probability that the person opposes a tax or is female? Give those a chance and then come back and see how you did. Okay, so the first one is probability that they support the tax right here or unsure. And if I look at these two events are mutually exclusive, so I simply add them up. One, support the tax or unsure. 396 plus 27, 423 out of the 1048, 40.4%. Last one, so I'll erase my color so we can, is going to be opposes the tax or is female. So oppose the tax is right here, female right here. I see there is overlap between those. Those two events are not mutually exclusive, so I'm going to have to subtract out the intersection. Opposing the tax was 625. 555 were female, but 300 of those were double counted by the intersection. So I add them up, subtract the 300, I get 880, divide by 1048, and that leaves me with an 83.4% likelihood that someone opposes a tax or is female. And there you go. That's how the addition rule for probability works. Thank you very much and have a good day.